This is Lab 4 for Physics 2212 on circuits. This lab was about circuits, and the main purpose was to predict how circuits with resistors in series and parallel would behave. This behavior would fall under conservation of energy and include the loop rule. We also looked at capacitors and specifically how they are charged and discharged and the time dependence of that. We also looked at conventional current and potential voltage difference and then used a computer simulation and our own calculated values and compared those. Some of the important physics concepts covered in this lab were conservation of charge and energy in series circuits. These conservation rules say that the charge passing through any point of the circuit at a given moment must pass through any other point during that same time interval. This is conservation because if it were not true, that would mean that a charge would be lost or gained somewhere in the circuit. Another important concept was resistor and capacitor circuits in which voltage has a relationship with time across a discharging capacitor. This is because we are no longer assuming that EMFs and resistances are constant in time, and therefore current and potential are no longer constant in time either. These graphs show how voltage can display time-dependent behavior. The first circuit we looked at had two 1.5 volt batteries, two resistors in series, and two ammeters. We were asked to predict the current I1 and I2 measured by the ammeters. As seen, the ammeter read 0.02 amps, which matched my calculation using V over R of 0.204 amps, or 0.0204 amps. This number is positive because I flows through the positive terminal. Also, when switching around the ammeters to be backwards, they still read 0.02 amps as they measure magnitude. Next, we replaced one of the ammeters with a voltmeter. This voltmeter measured the voltage drop to be about 3 volts, the combined voltage of the two 1.5 volt batteries. Because this is no longer a closed circuit, the ammeter read 0 amps. After removing the voltmeter, I measured the potential differences along the circuit using V equals IR for these certain points. When these were summed using the principles of the loop rule, the net voltage was 0 as predicted. The graph on the right shows the potential versus position around the circuit. As seen, the voltage climbs to 3 volts from the two batteries, that's between A and B, and then drops over the resistors, or between C and D by about 1 volt and between E and F by about 2 volts, after which it reaches 0 volts again. When attaching the voltmeter after altering the circuit, the ammeter reading will not change as it depends on voltage and resistance, which stayed constant. When placing the voltmeter on the 100 ohm resistor, the ammeter continued to read 0.02 amps, which confirmed my predictions. When replacing the voltmeter with an ammeter in parallel, we now see a reading of 0.06 amps because the current takes the path of least resistance. Next, we calculated the resistance for some elements of the circuit. For the 47 ohm resistor, I got 47.95 ohms, and for the 100 ohm resistor, I got 150 ohms, and for both the wire and meter, I got 0 ohms, and that's because the delta V was 0. The RC circuit had a 10 ohm light bulb, a 9 volt battery, and a 200 microfarad capacitor. As seen in the video, the light bulb was bright at first, but it dims as the charge collects on the capacitor. Eventually, the light is off when there is no longer a current. Current decreases as the capacitor charges. Next, we removed the battery from the circuit and connected the light bulb to the capacitor. There was still a charge stored on the capacitor, meaning the same situation happened where the light was bright and then dimmed as the current that went through the circuit went back to its original value and then discharged slowly. For the time trials, charging and discharging with the 10 ohm light bulb should have been the same, and charging and discharging with the 20 ohm light bulb should have been the same, but differ due to human error in my reaction time. Next, we set up a circuit with a 9 volt battery, a 200 microfarad capacitor, and a 30 ohm light bulb. We then timed the discharge of the capacitor and plotted the data for 90 seconds. The slope of this graph is -1 divided by R times C. So we can then solve for R times C, which was about 5.84 seconds, which is relatively close to our theoretical value of 6 seconds. Some final questions asked about this situation in real life using an actual ammeter instead of a simulation. And in real life, the resistance would be higher and the ammeter readings would be lower versus in our simulation. In terms of using a real battery to charge a capacitor, we would be interacting with resistance that comes from other parts of the circuit, like the wire, meaning the capacitor would not be fully charged instantly as suggested by an ideal model.